Today, I'm going to give final touch to my discussion on chi-square test. Okay. And in tomorrow's class, in today's class, you are going to learn some other aspects of chi-square test. And I think you will be enjoying today's class because various other intricacies of the test statistic and as well as the this as well as there will be a few discussion on the usage of softwares and some other things that I'm going to discuss today. And with this discussion, I'm going to bring the final curtain down on chi-square test. Okay. And to begin with, as you can see, I'm actually preparing the note and I'm modifying actually the earlier prepared note on chi-square test. I am introducing various other points over there. So in the beginning of this note, I have mentioned what is the basic objective of chi-square, as you can see. So let me read the basic objective of chi-square. It is in this particular type of problem, we consider a population in which each member has any one of k possible values, and we show how to test the hypothesis that a specified set of probabilities represents the proportions of the members of the population that have each of the different possible values. This is the basic objective of chi-square test. And I hope you have also gone through my earlier uploaded videos in YouTube. If not, then you must go through them because my previous few classes are based upon chi-square test. And if you do not, if you have not still watched my chi-square test video 1, then probably will not be able to understand anything in this part of the discussion. All these problems that I'm scrolling, all these problems have been discussed so far in your class or in section B. And the problem that I discussed in section B in my last class is this problem where we actually formed a 2x3 contingency table. If you have watched my video, you are going to understand what do you mean by a contingency table. Otherwise, you are not going to understand. So we formed a 2x3 contingency table, and I showed them how to apply the contingency table to test your null hypothesis on the independence of attributes in terms of chi-square test. Okay. And this problem has been explained. Now, in this particular problem, there is one part that I need to tell you today, because my today's problem, first problem, is based upon the change of that part. As you can see, the table that is in front of you, contingency table, where two characteristics are present. If I choose a sample from the population can be consisting of either male or female. This is one characteristic, and whether they are male or female, they will have different political affiliation towards some party. So their political affiliations are shown in the column. But what is important in this particular problem is that you see the totals of each row and the total of each column, they are different, isn't it? The total of each row and total of each column, they are different. And all these values that I have written over here, from starting from this cell 68 till 20, these are all observed frequencies. Although the row totals and the column totals are different, but total of the column total and total of the row total are same, which is 300. That which means the 300 people have been questioned, and the null hypothesis is based on the sample of size 300. Okay, why am I showing this to you? Because in my today's problem, I'm going to modify the thing a little bit, where you see my heading is chi-square test where marginal totals are fixed. So what do we mean by marginal total? Marginal total means, so okay, I can show you this chart. As for example, in the previous problem, I calculated the expected frequencies in the following manner. but you see the totals over here, the column totals and the row totals, they are different, although the sum of the column totals and the sum of the row totals, they are same. Now, these column totals and these row totals, these are called the marginal totals, but they are different. Now, in my today's problem, I'm going to take an example where the marginal totals will be fixed, and we'll try to see whether we can apply the chi-square test statistic to these cases or not. So this category is also falling under the section of test of significance of independence of attributes. The problem that I have selected is the following. A recent study reported that 500. Now you see, I have highlighted the number 500 over here. A recent study reported that 500 female office workers were randomly chosen and questioned in each of 4 different countries. Okay. One of questions related to whether these women often received verbal or sexual abuse on the job. The following data resulted. So reported case in Australia is as follows: 28. Reported case in Germany is 30. Reported case in Japan is 58, and reported case in United States is 55. And the question is, based on this data, is it plausible that the proportions of female office workers who often feel abused at work are the same for these countries or not? This problem is associated to #MeToo movement, which you are familiar with. Now, this problem is important, and I have selected this particular problem because of the fact in this category of marginal totals, because of the fact that, in this type of sample survey, which is a bit sensitive, not all workers come forward to tell their stories. Okay, so we do not have much sample. Okay, so we have a portion of the sample, the other portion have to be assumed or calculated theoretically. Now, we have the reported cases of this type of abuse from these countries, but those who in this 500 female office workers who are not saying that they have been abused in either way, maybe they definitely haven't been abused, or maybe they are telling lie, or maybe they don't want to say anything. They have put no comment in the form. Okay, so what we have only this particular values data. Now we will set the null hypothesis first of all as follows. In the null hypothesis, we will write that the proportions of abused female workers in these countries are equally probable. Okay, this is my because the null hypothesis is the hypothesis of no difference. So we always, and in other words, we use the equality symbol in null hypothesis. So that means that these two this particular countries in this particular countries, the reported cases are equally probable. Okay, and against the alternative hypothesis that they are not. Now we are going to form the we are going to form some order of contingency table, and that contingency table I have formed in the following manner. Now carefully observe. I am interested about the statistics. I was interested about the problem, but the problem part and the relevance and the significance of this kind of study has been discussed. Now I am interested in dealing with the problem with our known knowledge of statistics. Now, if I want to formulate the contingency table, what we have in front of us, let's see. What we have in front of us is that this marginal total, row marginal total, that is fixed. Okay, so these are all 500, and we have only this data: 28, 30, 58, 55. Now the not reported cases that have to be calculated from these marginal totals. So we will theoretically calculate the not reported cases, as since the reported case is 28 out of 500, not reported case is 500 minus 20, that is 472. And in similar way, we have calculated all the not reported cases over here. But these not reported cases have not been, although they are my theoretical frequencies, they have not been obtained directly by asking. These 472 people, those people that who do not have any problem, those female workers who do not have any problem, there may be three categories. Either they have not come forward to tell their truth, or they have written their in the section no comment, or they have told a lie, or maybe they are definitely not being abused. So, or maybe they are thinking that they are not being used. So there are various cases. So this is a theoretical value that I have calculated from just subtracting the lower one from the higher one. But I have to keep in mind that this marginal total is fixed. Now this marginal total, these are also marginal totals. Column totals are also marginal totals. In this case, the problem is set in such a way that the column totals are not are coming out as different. But if you arrange this particular data column wise, then in that case, your column totals will be fixed, your row totals will be different. Okay, so that is the matter of how you arrange your data, row wise or column wise. But the main important part is that this particular section is fixed. Now, this is the contingency table of order 2 by 4 for observed frequencies or theoretical frequencies. Now we are going to calculate the expected frequencies. Now those who haven't gone through my earlier videos, for them I'm just briefly saying that how do we calculate this part. How do we calculate this part 42.775 or this part? So what we do is that to calculate the expected frequency, we first of all, we put all these cell blanks. Okay, now suppose we want to calculate the expected frequency of this particular cell. So what we do, we have a formula which goes like this: Eij is equal to Nimj by n. So n is your 2000, this is your 2000, n is your 2000, and ni is related to the column total of the row. So this is your n1 and this is your n2, and this is your m1, and here all the mj's are fixed. This is your m2, this is your m3, and this is your m4. Okay, so if I want to calculate E11, what we do, we write n1 m1 by small n, and this means 171 multiplied by 500 divided by 2000, and thus we get 42.75. And since here 500 is fixed and corresponding to 171, all these column totals are fixed, so all these values will be same. All these values will be 42.75. So these values are same over here. Similar is the case with the second one. So suppose you want to calculate the expected frequency for this cell. So what we do, we write E22, and that is equal to N2 M2 by N. Now what is your N2? Your N2 is 1829. Your M2 is again 500, and your small n is 2000, and thus we get 457.25. And since the marginal column marginal totals are fixed, then we actually this all expected frequencies are actually same. So in this manner, we have calculated all the expected frequencies corresponding to each observed frequencies. Okay, so I hope you have understood what I mean to say over here by these calculations. Now, once we calculate the expected frequency and the observed frequency, one fundamental point that needs to be checked is that, and it is a kind of a checking criteria, that whether your total observed frequency and total expected frequency, they are same or not. So we need to check whether double summation over ij of nij and double summation over ij of eij, whether they are same or not. And in this case, we find that these two values are same, 2000. So that means we are moving in the right direction. Now, what I have done is that after getting these values, what you can do, theoretically, what we can do is that we can calculate the chi-square statistic, and the formula of the chi-square statistic is given as follows. So it goes like this: double summation over ij, nij minus eij whole square divided by eij. What does this mean? This means that you have to consider each nij and its corresponding eij, and you have to subtract it. Say, for example, 28 minus 42.75. Take the square of this and divide by the expected frequency, which is 42.75. And you go on like this. And I am going to write the last one, means this one, 445 minus 457.25 whole square divided by 457.25. And once you calculate all these 8 values, then you get some value for your chi-square statistic. So we need to do this this big calculation manually. So I have tried to take the help of a software called Maple. Yesterday I showed how Maple works in my video. I have with me the Maple software. I used to do lots of linear algebraic calculation with Maple, but Maple can also do the statistical calculation. Okay. So why am I at one point of time, sometime I told you that one day I'll show you how we can use the statistical software. So how can we can take the help of software to do the statistical calculation. So I think now is the time to show this to you. And at one point of time, if you are doing real statistics, you have to take the help of the statistical software. So what I have done, I have given the values as input. As you can see, the way I have taken the inputs, and first of all, this observed frequency matrix have been typed in and printed over here, and this expected frequency has been typed in and printed over here. And this is the command for testing the independence of attribute for chi-square with respect to chi-square test, and the level of significance is taken to be 5%. Now, if I use this command after and put a semicolon and enter, we get these values. What information we are getting from here? We are getting, first of all, although it is written in the following manner, that hypothesis is false and so, but we'll try to read it from right to left, not from left to right. So first we are getting the value of the statistic. That means if you calculate if you do the calculation manually that I have just shown you, you will get this value, which is 19.51. P value is given to be 0.0002144, very large number. Okay, P value. I'll come to that point later. The distribution is chi-square that I have used. So this information is given. And what else is given? It is a number is given. This number is 3. How it is 3? My order of the contingency table is 2 by 4. This is the order of the contingency table, order of the matrix. Now, the degree of freedom in this case, if the order, the formula is, if the order is R cross S, the formula, the degree of freedom formula is R minus 1 into S minus 1. And therefore, with respect to this formula, we get 2 minus 1 into 4 minus 1, which is 3. So we have to take the help of the chart or whatever. We have to keep in mind that the tabulated value is studied at 3 degrees of freedom, at this degree of freedom. So therefore here the number 3 is being shown, and this is the critical value. You can get the critical value, although it is very precise, because I have used the statistical table, but sorry, I have used the statistical software, but if I use the statistical table, this value will not be that precise. You will be getting some value up to keep where up to 3 decimal places they have considered, or 2 decimal places they have considered, but it is so precise because we have used the statistical software. And we know the basic rule that of rejecting or accepting the the null hypothesis related to chi-square, that if chi-square calculated is greater than chi-square tabulated, we reject our null hypothesis, or if chi-square calculated is less than chi-square tabulated, we fail to reject our null hypothesis. So here you see this is larger than this, and so you are rejecting the null hypothesis, and therefore it is written here that null hypothesis is false. Okay, so this is the meaning of the output that we have got after using this command. Now after this, what I have done is that I changed a little bit. I wanted to show you something, so therefore what I did is that I changed my level of significance. Now what change, if I change my level of significance, what other changes have occurred in the output? Everything remains same, but you see the critical value is changing. Now here also the calculated value of chi-square is greater than the critical value, so null hypothesis is false. Again, I have changed my level of significance. Now the critical value is 6.25. So again, the calculated value is greater than the critical value, null hypothesis is false. But now I have taken the level of significance as 0.0002. What is happening? Here you got the level of significance to be the 0.0002144440. If I try to be more precise, this is the level of significance, the lowest value of the level of significance at which the null hypothesis would be rejected. And you know that any value, any level of significance higher than this will make you reject the null hypothesis. So all the level of significances, 0.05, 0.01, 0.10, all these level of significances are much higher than this precise value, p value. But this level of significance that I have considered over here, 0.0002, this is less than this precise level of significance. And therefore you see at this level of significance, the critical value is coming out to be 19.65, which is greater than the calculated value. So calculated value is lesser and hypothesis is being accepted. I have done one more thing over here. I have taken the level of significance to be 0.001, 0.0001, which is further lesser than this particular precise level of significance. And you see, in all these cases, the null hypothesis is being accepted. So this particular homework is actually being done to show you how the level of significance plays an important role in deciding the fate of the null hypothesis. Okay, I have talked about level of significance in various different points of time, but here with the help of statistical software, I wanted to show you that how your conclusion is being affected by choosing an appropriate level of significance depending upon the p-value. P-value is also a kind of probability because it is a level of significance. It is also a kind level of significance because it is the least level of significance. Now here comes the important part. The important part is that now suppose you do not have the facility of using the facility of using any of the statistical software. So what do we have with us? We have the statistical table. This is the I know that there are many students who are not able to attend the online class because they are actually residing in remote areas. So they are facing troubles. Many of the students are participating with the help of mobile phones. And so for them, the statistical software will not work. They are not having access of the statistical software. So how will they do the calculations? Their calculations will not be affected because the statistical software is not available. They can take the help of the chart that I have provided you. This is the section I have cut and pasted over here from the chart. Small n represents the degree of freedom or the sample size, and these are the different levels of significance. Now you see, whenever you calculate this test statistic 19.51 or 19.51 at whatever level of significance, you are going to check this calculated value with the tabulated value. Now, if I consider this level of significance, you see this calculated value 19.5 is greater than this. This calculated value is greater than this also. This calculated value is greater than all the values in the chart. The highest value that you can see on the chart for corresponding to 3 degrees of freedom is 12.84. And therefore, for all these level of significance, you will say that your null hypothesis is being rejected. Okay, that much you can say. That much you can say about your null hypothesis if we use the statistical table. Obviously, the person who is using the statistical software will be in an added advantage. There will be an added advantage for him. Here, if you have this statistical table with you, and if I ask you to calculate the p-value, you'll not be able to get the p-value at all, because you know that this much value you are getting from 0.995 to 0.005. Now, other values are not there, but p-value is coming at 0.000214444. So it is somewhere on the right-hand side of the table that has not been printed. So if, unfortunately, if you have the access of the statistical table, and if I give you this particular problem and ask you to calculate the p-value, although you know that statistical table always do not give you the p-value, they only can give the range. But here also you cannot have the range at all because the values are not known. So what you can do is that you have to rely on the statistical table, and you will say that with respect to the table and with respect to all the existing values, my null hypothesis is always getting rejected. Okay, my null hypothesis is always getting rejected. You can do up to this, and no, you will not be able to find the appropriate p-value for this calculation. You will not be able to find the appropriate p-value for this particular problem. So keeping this in mind, the question setter has to be, cautious enough that there may be some students who are getting the help of statistical software and who are not. So in that particular case, what you can do, he has to put his question, he has to ask his question in a certain way by which nobody should be affected. Nobody should be affected by not having the statistical software at hand. What minimum thing that we can say about this particular calculation? Now, I'm activating the chat box so that you can put your attendance over there. Just a minute. Now, chat box is activated. You put your attendance. What minimum thing that we can say about this particular problem? We can say that, at least we can say that we know, since for all the existing values, the statistical software, is not available, and for statistical chart is showing that my null hypothesis is being rejected. So p-value is somewhere lying beyond 0.0005. It is lesser than 0.005. So he will write that if I ask him the same question, he is going to write p-value will exist below somewhere below the point that much he can say. Okay, that much he can say. Or he can do one another thing. Now, the person who is not having the desktop at all or laptop at all, he has to rely on this particular chart. No other way out. But suppose you do not have the statistical software, but you have a desktop and a laptop, then there is a way out. There is a way out, but the minimum requirement is you need to have a desktop or a laptop. Okay, otherwise not. Now I'm going to talk about this sometime later, okay, in today's session. So this is the thing. So statistical software somehow is calculating the p-value. How they are calculating the p-value, I'm coming to that. I'll come to that point also, don't worry. And how this statistical software is so precise in calculating the p-value, I'm coming to that point. But before that, let me show you something else. And also I'm going to give the answer of the question that I have raised over here, that what is the way out if I have at least one desktop or laptop. Now, what is the definition of chi-square variate? The chi-square variate, the definition, ultimately, we have done so many examples. So the chi-square, what is chi-square variate? So chi-square variate is nothing but the square of the standard normal variate, okay, with 1 degree of freedom. So if I explicitly write the definition of chi-square, it goes like this. So this is a normal variate, capital X, which follows normal distribution with mean mu and variance sigma square. And we know that we can standardize this normal variate with the help of this rule, where I'm changing the origin to the mean point mu, and I'm changing the scale with respect to the quantity sigma. And Z is the standard normal variate following normal distribution, it means 0 and variance 1. Now, if I take the square of this normal variable, we get this x minus mu by sigma whole square. Since there is one normal variable and only one, so there will be only one standard normal variate, and thereby we'll be having only one square standard normal variable square. So degree of freedom here is 1. Now, instead of taking only one normal variable, if we consider small n number of normal variables which are independent also, means the samples, if capital Xi represents the sample which are being drawn from the population, each sample are independent with mean mu I and variance sigma I square, each depending upon the drawing, the number of drawings. Then for each normal variable xi, they will be having the standard normal variable zi. And if I consider for each normal variable xi, if I consider the standard normal variable zi, and if I take the square of this and take the sum of this square, so chi-square is actually z1 square plus z2 square plus z3 square and so on up to zn square. Such a variate is called chi-square variate with n degrees of freedom, because there are n normal variate. So this is the definition of chi-square variable. And this is an image. This is an image that I'll explain that image in my next session, not in this session. This is an image of the chi-square variable, the probability distribution of chi-square. This is the graph that you will be having, okay, and for several different values of nu, this quantity is nu over here. This is actually the sample size. The thing that I have written here as n, they have used the letter new over here. So for different sample size 1, 2, 3, 4, these are the different uh, plots of the chi-square variate. The plots have been obtained with respect to this function. Okay, so I'm going to explain this in my next in more details in my next session. This is where I've just pasted the image from the Maple part. And lastly, before I conclude my first session of today's class, we have this theorem in front of me. Okay, so the theorem says that in a random and large sample, we find that the following expression follows chi-square distribution approximately with k-1 degrees of freedom. And you see, just look at the expression that I have obtained. Ni minus npi whole square by npi. Now, are you familiar with this particular expression? Yeah, of course, I'm familiar with this particular expression. Why? Because whenever we calculated the expected frequency, we use the formula NP. We use the formula NP, and therefore this is my expected frequency. You can consider this to be my expected frequency. This is my observed frequency, and this is my expected frequency. So what ultimately what we are getting, Ni minus Ei whole square by Ei for unidirectional case, and Nij minus Eij whole square by Eij for my bidirectional case. So why am I using, if someone asks me that why are you calculating the expected frequency by multiplying probability with the sample size, this is the reason why we can do so, because this theorem is there with us. The theorem says that if the random sample is taken, if the sample is very large, then chi-square distribution will follow with k-1 degrees of freedom. K are the, what is K? K is the different possible values that population parameter can take. Okay, so it will be k-1 degree of freedom for which the chi-square statistic will take this particular form, which has been used to deduce different types of formula that we so far have used in dealing with different types of problems in chi-square statistic. Now I'm stopping over here at this point. In the next session, I'm going to discuss this chart that has been pasted over here, and how p-value is calculated, and what is the way out if you have the desktop and laptop, and what minimum thing you can say about your p-value in a statistical calculation in chi-square.